Alright guys, today we are talking about piecewise functions. Okay, so real quick, let's give ourselves a formal definition. A piecewise function is a function, clearly, that is defined differently on different parts of the domain. So graphs of piecewise functions look like this. Right, maybe over here we have some part of a line, and then maybe in the middle we have a part of a quadratic, and then maybe we have like a constant line. Who knows, right? We could have all different things, but what makes this a piecewise function is that it's different on different parts, right? From here to negative infinity for x values, we have the shape of a line, right? The value of our function is a line. Between this x value and this x value, we have a quadratic. The value of the function is quadratic. And then from this x value onward to positive infinity, it's a constant value. So to evaluate a piecewise function, determine the piece of the domain that includes your input value. And plug into the associated function. So let's look at one of these. Let's start with a really simple one. Let's say we have f of x equals 3x and x squared. It's equal to 3x when x is less than or equal to 1, and it's equal to x squared when x is greater than 1. So this is the piece of the domain that this is the value of the function for. So value of the function. So what does that mean? Let's look at this. So if we were asked, what is f of negative 2? Well, our input value is negative 2, right? X is negative 2. So we need to figure out which piece of the domain we're looking at. Negative 2 is less than or equal to 1, so we want to use this value for the function. So we use this 3x, so we have 3 times x, our x value is negative 2, so we get negative 6. If we were asked, what is f of 2, then which piece of the function would we use? Well, we're definitely not less than or equal to 1. 2 is greater than 1, right? Our x value is greater than 1, so we want to use this value for the function. So we have x squared. X is 2, so we have 2 squared. We get 4. If we're asked what is f of 1, well, both of these have 1, right? But this one needs to be strictly greater than 1. 1 is not greater than 1, right? 1 is less than or equal to 1, so we want to choose this first one. So we choose 3 times x. X is 1 here, so we have 3 times 1, which is 3. Okay, let's say we were asked for what x values does f of x equal 16? Now, this is a little bit trickier. We're not given an x value, so we don't know exactly which piece of the domain we want to be looking at. So that actually means that since we're looking for the x values where we have a specific y value, we need to look at all the different possible values for the function and see when they're 16. So we need to set both 3x, right? That's the first possible value for the function, right here, equal to 16. And we also need to set x squared equal to 16. So we start with 3x equals 16. Again, we know that this is for x values that are less than or equal to 1. Let's solve for x. 3x is equal to 16 when x is 16 over 3, which is approximately 5.333, repeating. Okay, 5.333, is that an x value that's less than or equal to 1? Definitely not. So this is not a correct answer. We don't use this one as an answer because this x value doesn't fall within the associated piece of domain. Right, it has to match up. All right, let's look at this one. So, in order to solve a function like this, we definitely want to square root both sides. I take the square root of the left side. Square root and squared kind of undo each other. On the left side, I end up with this square root of 16, which is plus or minus 4. So that means I have x equals positive and negative 4. But remember, we need to check whether this falls into our associated piece of domain, right? Our domain here is x is greater than 1. Are both positive and negative 4 greater than 1? Definitely not, but positive 4 is. So positive 4 works here. So only x equals 4 falls within the associated domain. So our answer here is x equals 4. That is the only x value that we can plug into the proper piece of the domain that we can plug in that would give us 16. Now, can we see that graphically? Let's take a look. If we were to graph this function, how do we graph a piecewise function? Well, it's not terribly hard. It's like graphing kind of two graphs at once, in a way. So I'm going to start out in pencil. So we know that part of our graph is going to look like 3x. What does 3x look like? Well, it looks like a line, right, with a slope of 3 that passes through the origin. So a line with a slope of 3, our rise over run is going to be 3. So rise is 3, run is 1. So we have something like this, right? But remember, we only look like 3x for the x values that are less than or equal to 1. So we only look like this until this x value here, 1. So all of these x values, right, are included, right? Our domain where this is what our function looks like stops at x equals 1. All of these guys are included, but all of these guys are not, right? Okay, let's think about what x squared looks like. X squared has that parabola shape. We've seen so many parabolas so far, right? We look something like that. But remember, we only have this parabola shape for the x values that are greater than 1. So x values greater than 1, our first one starts right here, but is not included, right? Because we are strictly greater than 1. And then we include all of these guys, right? Greater than 1. Now, where would the value of this graph be 16? Well, definitely like some large number that's really kind of high on the graph, right? We can see that the pencil might hit it at certain places, but remember, the pencil is not actually part of the graph. The only part of the graph is the pen. So the only part that the pen is going to end up hitting it is at 4, right? So the pencil would probably hit it at x equals -4, right? That would be that left side of the parabola that's in pencil. And then our line 3x might hit it eventually, right, at 5.333, but those parts are not actually part of the function, so the only x value that is correct is 4, because that's the only x value that is within the proper domain. So everything else is not included, so we can kind of just erase it. And that's what our graph looks like. Awesome. Let's look at another one. Let's say we wanted to graph the function f of x and then we had, let's say, -2. We had one part that was x minus 1 squared, x plus 1 squared plus 2. And then let's say we had one part that was x minus 3. Let's say -2 was the value of the function for x is less than or equal to -3. Let's say that x plus 1 squared plus 2 was the value of the function from -3 to +1. And let's say that x minus 3 was the value of the function for x is greater than or equal to 1. Okay, so this one is clearly more complicated than our last one. Let's take a look. I'm going to draw it nice and big. So 1, 2, 3, 1, 2, 3. So for all x values that are less than -3, so that's everything from here onwards, right? Okay, so our first function is just a constant of -2. So for every x value that's less than or equal to -3, right? For every x value that's to the left of -3, the value of the function is just -2. That's actually pretty easy, right? Everything to the left of -3 is just the value -2. So that looks like a straight line, right? Continuing off to the left. All right, so our next piece of the function, right, between -3 and 1, not including those endpoints, looks like this. This is a quadratic in vertex form, right? Where is the vertex of this quadratic? Well, our h value is -1, right? We have to flip the sign, and our k value is 2. So we have -1, 2. So our vertex is right here. I'm going to draw in pencil.
I wanted to draw in pencil here just because we're not sure if we're in the correct part of the domain yet. So before we put it down permanently in pen, let's do it in pencil.
So let's kind of graph this by point plotting. As I move to the left 1, right, as I'm looking at x value equals -2, let me plug that in for x, right? -2 plus 1 is 1. 1 squared is 1. 1 plus 2 is 3. So we have -2, 1, 2, 3.
So we've graphed the vertex and a second point on this parabola. Are they in the proper parts of the domain? Well, the first is x equals -1, and we also have x equals -2. Both of these are between -3 and 1, so we can put them down in pen. We can look at more values of the function that are between -3 and 1.
Let's look at 0. What happens if I plug in 0? Well, at 0, I get 0. Plus 1 is 1. 1 squared is 1. 1 plus 2 is again 3. So I end up again here, right? 0, 3. Okay, now as I move forward, right, to x equals 1, or backwards, right, in the negative direction to -3, neither of those are actually in the domain of my function. But I know that I'm including all of the x values right up to -3 and right up to 1. So I actually need to record those endpoints with an open point. Where is that open point going to be? Well, I can figure that out by plugging it into the function. So let's start with -3. If I plug in -3 here, -3 plus 1 is -2. -2 squared is 4, positive 4. 4 plus 2 is 6. So the function's value at -3 is not 6, but I do need to put an open point there. So I have -3, 1, 2, 3, 4, 5, 6. So right about here. Similarly, at x equals 1, this is not going to be the value of the function, but I do need to figure out where to put my endpoint, right? This open endpoint. So I have x equals 1. 1 plus 1 is 2. 2 squared is 4. 4 plus 2 is 6. So I also have the value of 6. So this open point is going to be at the point 1, 6. So that is about right here. So this part of the function looks like this. So that is the part of our function that is between -3 and 1. And both of these have open points because x is not equal to -3 or -1. right? At -3, we've already seen so far, the value of the function is -2, right? So this point is open and this point is closed. All right, let's graph this last piece. So this is for all of the x values greater than 1. So greater than 1, we're equal to x minus 3. X minus 3 is a line with a slope of 1 that has a y-intercept of -3. So that is going to look like this, right? Y-intercept of -3, and then over 1 and up 1 for each point after that. So here, here, here. Right, and normally the line would extend in this direction too, right? But, right, so this line, the line x minus 3 looks like this. Again, I'm drawing it in pencil. But we're only looking at the x values that are greater than or equal to 1. So greater than or equal to 1. Equal to 1 is this point right here, right? 1, -2. And greater than is all of these guys. And then everything else is not a point on this graph. So this is what the graph of this function looks like. All right, let's look at some applications in the lab manual. So this is from our section on piecewise functions in the lab manual for Module 2. I'm going to start a little bit further into the lesson, a little bit further into the problems with this question about the town of Cary and how they calculate cost for water usage. So the first thing I would like to do here is what we always do when we start with a word problem, which is identify the independent and dependent variables and what they represent. So what is the independent variable here, first of all? It's definitely not x. It's g, right? G. And our dependent variable is c of g. So here, what does g represent? Well, g represents the water consumption in thousands of gallons. So water consumption and the units are thousands of gallons. C of G here represents a citizen's cost for water usage before taxes. So I'm just going to say cost. And we can assume that's going to be in dollars. Okay, so first things first, we want to calculate and interpret C of 7.5 in this situation. So C of 7.5, well, C of some G is the cost for water usage for that amount of water consumption, right? So this is the cost that someone would have to pay if they used a G value of 7.5, right? Here, G is 7.5. It's not 7.5 gallons, right? Because remember, G is in thousands of gallons. This is 7,500 gallons. C of 7.5 is the cost of using 7,500 gallons of water. All right, so let's calculate it mathematically. So our G value is 7.5. We know that when G is between 0 and 5, this is the value of the function. 7.5 is not between 0 and 5, so this is not what we want to use. When G is between 5 and 8, we use this value of the function. 7.5 is between 5 and 8, so this is what we're going to use here. So the value of the function is 3.75 times g. Our g is 7.5 minus 5 plus 19.6. We plug all of this into our calculator. We've got 3.75 times 7.5 minus 5 plus 19.6. 1916. This gives us 28.535. All right, is this our answer? Yeah. How should we write it? Well, because remember, we're dealing with a word problem, so do we need to change anything? What does this value represent? Well, again, represents the cost of using 7,500 gallons of water. So this is money, right? So let's write it as money. $28, and we definitely wouldn't write 0.535 cents, right? That's going to end up being 54 cents. So that is our answer. Okay, use function notation to represent a citizen's cost for water usage before taxes if he used 8,200 gallons of water, and calculate that value. So we want 8,200 gallons, and we want the cost for water usage before taxes, right? Which all of this is before taxes, so we are okay. So that's definitely C of G for some G value. And what G value do we want to use? 8,200? That's going to give us too big of a number because remember, our units are in thousands of gallons. So here, right, how many thousands of gallons is this? This is going to give us a G value of 8.2. So we're looking for C of G when G is 8.2. In function notation, we want to write that as C of 8.2. All right, what is C of 8.2 equal to? It asks us to calculate that value. Let's check it out. Is this G value in our first, second, or third category, right? Does it fit into this piece of the domain, this piece, or this piece? The last one, right? 8.2 is greater than 8. So we want to plug into this part of the function. So we have 5.33 times G minus 8. G is 8.2 minus 8 plus 30.14. We plug all that into a calculator. We end up with 5.33 times 8 minus blah, 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 plus 30.14. We get 31.206. Again, we're dealing with money, so we want to rewrite this. We end up getting 31.21. That's our answer. All right, last but not least, how much water did a citizen use if her cost for water usage before taxes is $17.52? So this is one of those tricky ones where we're given a Y value, right? Cost for water usage is $17.52, right? Cost is our dependent value, and we need to find the independent value, right? When we did that in our notes just now, we had to check each part of the function to see if there was an independent value that gave us that dependent value. So we need to check each part of this function to see if it gives us 1752. So let's start with the first one. So we have 3.28g plus 2.76. We want to see if there's a g value that gives us 1752. Okay, let's check it out. So we solve by subtracting 2.76 from both sides. We get 14.76 over here equals 3.28 g. We solve for g by dividing by 3.28 on both sides. We get 4.5. So we got a g value. What are the constraints for this g value? Where does it need to fit? Well, the domain for this piece of the function is from 0 to 5. Is 4.5 between 0 and 5? Definitely.
So while we got g equals 4.5, it's important to note that, remember, g is in thousands of gallons. So our answer here is actually 4,500 gallons of water.
All right, let's check the middle part. Sometimes we can kind of assume that since we found one g value, it's not going to be any other g values. But in this case, let's go ahead and check all the different pieces just so we can see how that works. So the middle piece is 3.75 times g minus 5 plus 19.16, and we want to see whether we have a g value that equals 17.52. So we can start off by subtracting 19.16 here. We end up getting negative 1.62. We divide by 3.75. We get g minus 5 equals negative 0.437. Then we add 5 and we end up with g equals 4.563. All right, what are our constraints for this part of the function? The domain of 5 is less than g, but g is less than or equal to 8 as well. Does this work? Is this g value within this constraint? Definitely not, so this is not an answer. Last one. Okay, we want to check if this is ever equal to 17.52. We can start by subtracting 30.14. We get negative 12.62. We divide by 5.33. We end up with negative 2.368. Then we add 8 to both sides and we get the g value 5.632. The constraint here is that g is greater than 8. Is 5.632 greater than 8? Nope, so that does not work. Okay, the next problem I would like to look at is actually this one. So we have Marcus is moving. There's a company that charges $200.91 for 3 hours. After that, it's $54.99 for every hour afterwards. So we're asked to calculate Marcus's cost as a function of number of hours needed, h, and then we need to sketch and label the graph. So first of all, let's start out by looking at what our independent and dependent variables are here. So we're looking for costs as a function of number of hours needed. So C of h is what we're looking for. So our independent variable is h, and our dependent variable is C of h. H represents the time of work, right? Hours needed. I'm just going to write hours here because we have very little space. And then C of h is cost, and of course that's going to be in dollars. We're kind of being asked to create the function here, so we're going to end up writing something for C of h, some piecewise function, but we don't really know what yet. So let's give it a shot here. First of all, let's think about a couple of different values of our function. So let's say we have 1 hour, right? And we're trying to look for the cost after 1 hour of work. At 1 hour, how much is it going to cost for him to use this moving company? Well, it says they charge a blanket cost of $291 for the first 3 hours. So if he uses it for 1 hour, he still has to pay $291. If he uses it for 3 hours, he still has to pay $291, right? That's all the amount of time they'll charge $200.91, no matter what. So the value of the function here is 291. Okay, so let's think about something that's greater than 3 hours. Let's think about 4 hours. What's happening there? So for the first 3 hours, they've charged $291, no matter what. So we definitely have to start with that. And then after that, they're charging $54.99 for each additional hour. So if they're working for 4 hours, then he's getting charged $291 for the first 4 hours, and then an extra $54.99 for that 4th hour. What happens at 5 hours? Well, we've got $200.91, and then we've got $54.99, but for 2 hours, right? So $54.99 times 2, right? Let's graph this and see if that is helpful at all in trying to figure out what's going on here. So for our first 3 hours, right? 1, 2, 3, 4, 5, 6. Right, this is how much we're paying, $200.91, right? We're paying this much for the first 3 hours, 1, 2, 3. Right, so no matter if it's 1 or 2 or 3 hours, we're getting charged $291 regardless. The next hour, right, after hour 4, we get charged $200 plus $54, right? $54.99. So what is that? $200.91 plus $54.99 is $255.90. So that is our value for h equals 4. So our function goes like this. At 5, we have $54.99 for the first hour, and then $54.99 for the second hour after that, right? So what is that? Well, it should just be $255.90 plus $54.99 again. So we end up with $310.89. That's the value of our function at 5 hours. 6 hours, you better imagine that it's going to continue to rise just like this, right? As it continues onwards. So again, these are our number of hours worked, and this is the cost, right? C of H. So what's going on here? Let's look at C of 6. So C of 6, again, was just one more of these $54.99s tacked on, right? So this first one ended up being $255.90. Then we had $310.89, right? The next one was $200.91 plus $54.99 times 3, right? That's going to equal $365.88. So what's going on here? So we want to kind of extrapolate. So for C of H, where H is greater than 3, what is the cost going to look like? So for this first one, right, for 4, we had 54.99. As we continue onwards, right, this first one we had 1 54.99. The second one we had 2 54.99s, right? This third one we had 3 $54.99, right? So as we continue onwards, this number is getting higher for each hour we get larger, right? So what is this number? How is it related to H? Let's kind of visualize this. So we have 0 hours, 1, 2, 3, 4, 5, 6, etc. So for our first 3 hours, we pay $200.91. Then when we get to 4 hours, we have to add on this extra $4.99. Then with 5, we have another $54.99. And then with 6, we have another $54.99. Right? So with each hour onwards, we're adding on another $54.99. It's one $54.99 for every hour after 3. So for 4, it's 1. For 5, it's 2. For 6, it's 3. So it's H, right? This is our H value. It's H minus the first 3 hours, because that's already covered by this 291. So we have $54.99 for every H minus 3 hours, right? So $54.99 1 times, which is $54.99 times 4 minus 3, right? $54.99 times 2, 2 is 5 minus 3. 3 is 6 minus 3. So for each of these, we have 291 plus 54.99 times H minus 3. And this is the value of our function when H is greater than 3. So let's go ahead and write our function for C of H. Let's start out by writing our domain. So the first part of our domain is all of the hours before 3 hours, right? Can we just write H is less than or equal to 3? No, because then we would include negative hours, right? That's not going to count. They're not going to pay you for not moving your stuff. So we have h is also greater than or equal to 0. Then our second part of the function is for all the hours after 3. So h is greater than 3. What is the value of our function when h is between 0 and 3? Well, for those first 3 hours, as we've been saying, it's $200.91, regardless of how many hours less than 3 you have. What about h is greater than 3? So we have already written that, right? That's this 291 plus 54.99 times h minus 3. That's our function. So now we can use our function to work on these two problems. So determine Marcus's costs if he needs 1.5 hours of help. Easy. So 1.5 hours is our h. Now we're looking for the cost, right? So that's c of h. So that means we're looking for c of 1.5. 1.5 fits into this first part of the domain, which is a value of 291. Could we have figured that out without having the function? Totally, right? We would have just looked at the question and said, oh, okay, I know that I am only going to get charged $200.91 for the first 3 hours. So we could have totally solved this if we didn't have the function.
Please make sure you also write units of dollars on your answer here.
How many hours of help could he get if he had $500 at most for the move? Well, this is where we have to set equal to both pieces of the function, right? $500 is a dependent value. So is it equal to the first part of the function? Definitely not, right? This is just not true. So there's no h value that's going to make that true. What about the second part of the function? So 291 plus 54.99 h minus 3 equals 500. We subtract 291 from both sides. We get 54.99. H minus 3 equals, this becomes 299.09. Then we divide by 54.99. We get h minus 3 equals 5.439. Then we add 3 to both sides. We finally get h. We get 8.439. That means h is 8.439. What are the constraints on this? We want h to be greater than 3. So this checks out because 8.439 is definitely greater than 3.
And what are our units here? Well, remember we're working with h. So h is our independent variable, which is hours worked. So we can have 8.439 hours.
So that is the absolute most he can get help with if he has $500. Let's say we're looking at this question. I'm going to do this in the notes so that we have a little bit more space. So you have a summer job. We get paid $8 an hour and time and a half for overtime. So if you work more than 40 hours a week, full-time, your hourly wage is 1.5 times the normal hourly wage of $8. So 1.5 times the 1.5 times your normal wage would be, well, 1.5 times 8, right? So 12. So if you work more than 40 hours, you're going to get paid $12 for each of those 40 hours. So let's think about our independent and dependent variables here. So we want P, big P, in terms of the number of hours you work. So number of hours, H, number of hours worked, which is clearly in hours. And then we have P of H, which is your weekly pay. And that is in dollars. Okay, so let's think about this. Maybe it would help to draw the graph, maybe it won't. If it works for you, you can, I'm going to do it just in case that is helpful for folks, but you don't have to draw it if that doesn't help you. As we start off, of course, if I work 0 hours, I'm going to get $0, right? This is our pay, right? This is P of H, and this is H. For every hour I work, I'm going to get $8, right? So I'm going to do this every 10 hours. So let's see what's going on every 10 hours. So let's say we work 10 hours, 20 hours, 30 hours, 40, 50, 60, etc. So at 10 hours, again, I've gotten paid $8 an hour. So $8 an hour for 10 hours is $80, right? $20 hours at $8 an hour is going to be $160, right? I'm going to write this over here. So when H equals 10, right, we have P of 10, which is, we said 8 times 10, so 80. P of 20, right, we work 20 hours, is 8 times 20, which is 160. P of 30, same thing, right? And P of 40, same thing. So 240 and 320. So 240, 320. Let me draw that a little bit higher. This here, 40 is 320. So we have this nice upward sloping line for those first 4. What is the slope of that line? Well, if we work 1 hour, we make $8. If we work 2 hours, we make $16. That's a rise of 8 over a run of 1. So this slope is 8, right? It's increasing $8 for every hour. So for H is less than 0, and H is greater than 0 and less than 40, right, for the first 40 hours, P of H is just a line with a slope of 8, right? 8 times the number of hours we've worked. Simple as that. Okay, let's check out some times above 40 hours. So let's say we work for 50 hours. If we work for 50 hours, then we make that first $320, but then all of the hours after that, so there's 10 hours past 40, we're going to make $12 an hour. So we make 320 plus $12 an hour for those next 10 hours. What does that equal to? Well, 320 plus 12 times 10 gives us 440. 440 might be like here. So our slope gets higher all of a sudden. At 60, how much do we make? Well, we, again, make those same 320 for the first 40 hours. Okay, so then we make $12 an hour, right, for all of this time after 40 hours. So that's 20 hours, right? So $12 an hour for 20 hours is 12 times 20. So we end up with 320 plus 12 times 20, which gives me 560. All right, so what's going on here? So similarly to the last problem, this is for the payment when we work more than 40 hours. So P of H here, each time we have to add in that 320 for those first 40 hours. And then for the hours after, right? However many hours after 40, we have 12. So we have 12 times. How do we get 20 from 60 and 10 from 50? Well, we have to subtract out those 40 hours that were covered by this first part. So we have 12 times H minus 40. This is the piece of the function for H is greater than 40. All right, before we write that out, let's look at the graph. So at 60, we have 560, which is probably about here, 560-ish. So our graph, again, gets a little bit taller, right? We have this second part of the graph that has a slope of 12, right? We're increasing by $12 an hour. This part of the graph has a slope of 8. Functions, we have P of H, let's write it out. Okay, so for the first part of the graph, right, from 0 to 40, so H is between 0 and 40. We have $8 an hour, right? We said 8H. For our second part of the graph, we have 320 plus 12 times H minus 40. So 320 for the first 40 hours plus 12 times H minus 40 for those last bit. So I have H is greater than 40. This is my function. So it asks us, how much will you get paid if you work 55 hours? So that is P of 55. 55 is between 0 and 40 or greater than 40? 55 is definitely greater than 40. So we use this part of the function. So we have 320 plus 12 times 55 minus 40. We can plug that into our calculator. We end up with 320 plus 12 minus blah, 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 blah. We get $500. Exactly. So that is, the answer is $500 even. Could we have figured this out without having the function? Totally. If we didn't have the function, we could just think about how, okay, I know I'm going to get paid $8 an hour for the first 40 hours. So 8 times 40 is 320. And then for the next few hours, right, for the hours between 40 and 55, I get paid $12 for each of those hours. So I get paid $12 for those 15 hours. So 12 times 15 is 180. 320 plus 180 is 500. So we could have gotten this without the function, but nice to have the function as well. I know this was a long lesson. Hopefully it makes sense. There's extra practice with Desmos and then WebAssign. Thanks so much for sticking with it, and thanks for watching.